The purpose of this video is to discuss and validate the Sensor Skin, a senior project design sponsored by Aris Group LLC and facilitated by Grand Valley State University. I'll begin by introducing the members of our team. From left to right, Dr. Robert Bossmeyer, our faculty advisor, Tyler DeVogue, focused on firmware design, Mike Wolf, signal analysis, Robert Regal, housing and hardware design, myself, Matt Smith, electrical design, Joe Conklin, implementation and data collection, and Eric Bourne, Wi-Fi communication. The sensor skin is used to monitor the behavior of an appliance of interest and communicate significant events via Wi-Fi to the user. It employs an array of sensors that measure the characteristics of the appliance and its surroundings, and uses the data collected to determine its mode of operation. The user can place the sensor scan on a number of predefined appliances and even create their own using a cloud interface. Selecting a new appliance to be monitored initiates a Wi-Fi connection between the server and the hardware to auto-calibrate the sensor skin to its new appliance. The output of this project will be two devices, referred to as Phase 1 and Phase 2. Phase 1 will be a development device which is designed to facilitate the exploration of new appliances. Phase 2 will be an efficacy device which better illustrates an end product, as it's designed for smaller size and greater battery life. Shown here is a front view of the completed Phase 1 device. The water sensor, piezoelectric vibration sensor, accelerometer, and motion sensor can be seen mounted to the device, as well as the Wi-Fi shield and a photoresistor used as a mounting detector, which is mounted into the base of the Phase 1 device. And shown here is the back view of the same device. You can see the connections for the microphone, photoresistor used to capture magnitude of ambient light, thermistor used for case temperature of the appliance being mounted to, and the Teensy++ 2.0, which is our development board. Shown here is the completed Phase 2 device. As you can see, this is just the internal geometry of the housing as well as the electrical hardware stack up. All of this would be enclosed in the final housing design, which will be shown later in this video. As you can see, the device has shrunk significantly. This is to demonstrate the efficacy of the device from a consumer standpoint. This does encompass all sensors and all preamplifiers and circuitry that were available in the Phase 1 device. Some design choices were made to limit power consumption so that we can achieve maximum battery life. Shown here is the left side view of the same device, showing the connections for the thermistor, photoresistor, and microphone. And the right side view showing the connections from left to right for the photoresistor, which is the mounting indicator, as well as the water sensor. This video will now be used to validate the ability of the Phase 2 sensor skin to detect the different modes of operation for the 5 devices within the scope of this project, those being the garage door, sump pump, washer, dryer, and television. All devices will be powered by battery and communicate state changes using Wi-Fi. The first application in our scope is the garage door. In order to observe its behavior, we simply use an accelerometer to monitor its orientation. A vibration sensor is also used in order to detect when the garage door begins moving. This provides an interrupt signal and allows for the use of power down modes. In this first example, we'll watch the garage door move from closed to open and confirm that Wi-Fi communication is used to determine that the state has changed. Now we'll observe the garage door transitioning from an open to a closed state using the same sensors as inputs. The next application in our scope is a sump pump. And to identify different states for this device, we use a combination of two sensors, a water contact sensor, which simply identifies the presence of water, and a vibration sensor, which is a piezoelectric vibration tab used with a preamplifier to generate the characteristic vibration generated by the sump pump motor when turned on. The water contact sensor also is able to generate an interrupt to the microcontroller to wake it from deep sleep modes. In the first example, we will identify the off mode, characterized by no water and no vibration.
It is 5:07. I just connected the sump pump and it reported the first event, which is the initial state. The pump is off, no water is present, and that is because I have not yet placed the water sensor into the well.
In the next state for the sump pump, the water sensor will be placed in the reservoir, which is already filled with water, while the sump pump motor is unplugged.
So in this goes, and it is now submersed in the water, and we should be seeing the state change momentarily. Oh, here it is. The pump is still off. Okay, water is present, pump is off.
In the third state for the sump pump, the motor is plugged in, allowing it to turn on. Vibration and water presence will both be detected.
Okay, let's plug the pump in. Okay. You can hear it rumbling a little bit. Vibration is definitely present. And oh, there is our vent. Pump is on, water is present.
In the final state for the sump pump, the water contact sensor is removed while the motor is allowed to continue running. Vibration will be detected, but not the presence of water.
And now I will remove this so we don't have to wait until it drains down, and in a minute we should see our final event of this use case, which will be pump is on and no water present. Hey, there we are. Pump is on, no water present.
The next application in our scope is the washing machine. We use a microphone and vibration sensor in order to sample for a period of time and generate enough data for a frequency analysis. Based on the returned dominant frequencies of the device during different modes of operation, we can define states that can be communicated to the user. In the first example, we will define the off mode.
As you can see, the washing machine is currently in the off state, and when we look to our cloud interface, we can see that it is also in the off state.
The next state for the washing machine is fill mode, in which water is drained into the basin of the washing machine.
As you can now hear, the washing machine has now transitioned into the fill state. If we look over to our cloud interface, we can see that the state change has been noted here.
The next mode of operation for the washing machine is in running mode. This is characterized by lower frequency content detected by the microphone and vibration sensor.
You should now be able to hear that the washing machine has transitioned into the running stage. We can now see this on our cloud interface.
The next mode of operation for the washing machine is in spin mode, which is characterized by dominant higher frequency content.
The washing machine has now entered its final spin phase. You see it on the serial interface right there.
The fourth application in our scope is the dryer. Again, the vibration sensor is used to characterize the different modes of operation based on frequency content. In the first case, we'll observe the behavior of running mode. The second mode of operation for the dryer is off mode. This is characterized by low magnitudes of vibration, as well as a 60 Hz signal induced by the washing machine's power supply. The final application in our scope is the television. Once again, the vibration sensor is used to distinguish between states. This is done in this case by detecting the lower frequency content of the audio generated by the TV. To cover this range, high gain mode must be enabled by the microcontroller. Turning a single pin high allows for different circuitry to be used in the preamplifier configuration, allowing the vibration to be much more sensitive. In this case, we'll watch the transition from off to on mode.
Alright,
You filming?
the TV is off.
The second mode of operation for the television is off mode. With no audio, very little vibration will be generated, causing the dominant frequency on the output signal to be the 60 Hz induced by the nearby power supply. This is used to define the state for off mode.
No sleight of hand here, folks. TV is off. As you can see, the device just picked it up. And we are back on off on the server.